Okay, we're continuing on here, chapter 7, and we've been talking about types of reactions and ways to classify reactions. And as we've been talking about, there's really two big categories of reactions. There's double displacement reactions. And in a double displacement reaction, we basically have two ionic compounds. And what happens is basically we switch partners and we make two new ionic compounds on the other side. And that is sort of the big classification of reaction. And underneath this sort of classification are more specific ways you could classify double displacement reactions. One type of double displacement reaction is classified as a precipitation reaction. And in a precipitation reaction, basically one of those products, or maybe both, but in most cases, one of those products will make a solid. Now, remember that we can use solubility rules to help us decide what ionic compound would make a solid or not. And those solubility rules allow us to sort of make that decision when we sort of switch partners. Another one that we talked about at the end, I think last time, was acid-base reactions. And acid-base reactions are sometimes referred to as neutralization reactions. Uh, they typically will make water, and that's a result of the H plus from the acid basically reacting with the OH minus from the base to make the water. And as we talked about, really double displacement reactions account for 2 to 3 main reasons why a reaction takes place. And those 3 reasons, again, are you made a solid, you formed water, or you basically have an electron being transferred. So double displacement, like I said, kind of takes care of those 2 of the 3 reasons why a reaction takes place. The other sort of big category, which we'll talk about today a little bit more, is redox reactions. And in redox reactions, we have electrons being transferred. And that is sort of the third reason why pretty much reactions take place. Again, you can pretty much break down most reactions to those sort of 3 things. Either we made water, we made a solid, thank you, or we have electrons being transferred. The other thing that we talked about in relationship to double displacement reactions was that we can really write 3 types of equations that kind of explain what's going on. We could have, for example, our molecular equation where maybe we got something like sodium chloride plus some silver nitrate. And again, this is a double displacement reaction, as again, we have 2 ionic compounds going to switch partners here on the other side and going to make some silver chloride, which is a solid, and some sodium nitrate, which is aqueous based on solubility rules, that things with nitrate are aqueous. This is our molecular equation. And we can break this apart into our total ionic equation, and that is anything that is a strong electrolyte will break apart. So sodium ion, chloride ion here, plus some silver ion. Nitrate's going to break apart. I'm running out of room, so I'll go underneath. On this side, we have a solid, which stays together. So typically when you write this type of equation, anything that is a solid, anything that is a liquid, anything that's a weak electrolyte will stay together. So you typically don't break those guys apart. The sodium nitrate is a strong electrolyte, which will break apart as well. And this equation here, again, is what is known as the total ionic equation. And sometimes people will just call it the ionic equation or complete ionic equation. And remember that when you do write an equation like this, anything that is an ion does need charges. And when we look at this equation, we can find ions on each side of the arrow that are exactly the same. So in this case, we have sodium here on the left of the arrow. We have the exact same sodium ion on the right. We have some nitrate on the left-hand side of the arrow, and we have some nitrate on the right-hand side of the arrow. So these guys here are what are referred to as being spectator ions. So these guys are spectator ions. And spectator ions, much like the name implies, they're basically just watching what's going on. They are not involved at all in any of the products being formed. They're just, frankly, just floating around in the solution. So they're just floating around, swimming around in the pool. They're not coming together to make any type of product. And what we typically do with these spectator ions is we just cross them out on both sides. And by the way, they should completely cancel on both sides, which means you should have the exact same number of ions on the left and right hand side that are spectator ions. They should completely break apart. What we're left with is the third type of equation, which is the net ionic equation. And then in this case, it would be the silver plus the chloride is actually coming together to make our silver chloride solid. This is really the reaction that's actually taking place when you mix those two reagents of sodium chloride and silver nitrate. This is known as the net ionic equation. And it basically tells you exactly what's happening in this reaction and what is going on. And as you can see here, this is really the solid being formed, which again is the reason why this reaction is taking place. And it is the formation of this precipitate that's actually going on here. So this is a precipitation reaction, also still a double displacement reaction. Any questions on any of that part there? All right. All right, so we were kind of talking here at the end about strong acids and strong bases and the reaction that undergoes. And again, whenever you have a strong acid plus a strong base, you will always form two things. You will always form water and a salt. And in this case, this is our strong acid, which is our HCl. This is our strong base, which is our sodium hydroxide. That obviously is water. And this is our salt here. And again, if you kind of go through your total ionic equation, this is what we're going to get. Here again, we do not break apart water as it's a pure liquid, so we keep water together. We again can find our spectator ions by looking on either side. And again, there's a sodium ion on the left and right. There's a chloride ion on the left and right. And again, those are going to be our spectator ions. By the way, pretty much spectator ions will come from the salt in this reaction. The salt is basically your spectator ions that are going to be there. And again, just like before, we're going to cancel out our spectator ions on both sides. And that's going to leave us our net ionic equation here for this reaction. And that is, again, the H plus from the acid and the OH minus from the base coming together to make water. Again, the formation of water here, one of the three reasons why a reaction takes place. And really what is happening when you take an acid and base together, you're making water. And that is ultimately what is happening. You could take, as I might have mentioned at the end last time, you could take really any combination you like of a strong acid and a strong base. And when you put them together and you go through these three equations, you will always end up with the same net ionic equation, which again is the formation of water. This again is why this is sometimes referred to as a acid-base neutralization reaction, because you are basically making water in this case. Any questions on that there? So here's a couple of other examples. Again, this is nitric acid, which is our acid, our strong acid. There's our base. Once again, here's the formation of water and our salt. These again are still double displacement reactions, even though they're more specifically classified as acid-base reactions. We are switching partners, H plus and OH minus, going to come together here to make our water. And then obviously the other part there is going to make our salt. The K plus is going to come together with the nitrate to make our potassium nitrate in this case. And again, we have that exchange of ions happening, going this way and going this way, basically. Now, I would say probably in most cases, the salt that you form as a result of this reaction will be soluble and be floating around as ions. It is possible that you could have an insoluble salt, but it's, I would say, very rare that perhaps you would come across any of those. So usually the salt, based on solubility rules that we talked about, will be soluble. And that's what we see here. This, because it has chloride, is going to be soluble because it is not with silver, lead, or mercury. This, because it has nitrate, will always be soluble because, again, there are no exceptions for nitrate. All right, so that wraps up sort of the double displacement part of reactions. We're now going to talk about redox reactions. And redox reactions, again, are the big classification of reactions, and they really account for electrons being transferred. And that's ultimately what is happening in this case. So redox is sort of a short abbreviation for the two things that happen in this type of reaction, and that is oxidation and reduction. And when something goes through oxidation and something goes through reduction, they always occur together, which means if one thing is being oxidized, the other thing is being reduced. So they always sort of happen together. When something goes through oxidation, or if something is oxidized, it means it has lost electrons or will lose electrons. And when something goes through reduction, it means it has gained electrons. There are definitely other definitions of oxidation and reduction, which you really don't come across too much in general chemistry. If you continue on to organic chemistry at some point, you'll see some other definitions of oxidation and reduction, which is gaining oxygen or losing oxygen, or gaining hydrogen or losing hydrogen. But most of the time here, we talk about electrons. So what does that mean? It means, for example, if we have a reaction, we could kind of determine what is going on in terms of electrons, who's losing electrons, who's gaining electrons by doing so. One of the easiest ways to sort of maybe figure that out is when you look at an element on like the left-hand side of the arrow versus that same element on the right-hand side of the arrow, you could look at what is known as oxidation number or oxidation state, which essentially is similar to its charge on both sides of the arrow. And you could actually use just a basic number line to help you decide what is going on. And usually on a number line, there's positive numbers to the right there. There's negative numbers kind of to the left of zero. And if you look at sort of the oxidation state or sort of charge of an element on the left-hand side of the arrow and compare it to what is happening on the right-hand side of the arrow, and if it is moving in the positive direction, then that substance is going through oxidation. Because when you lose electrons, you now have more protons than electrons, so you now become more positive in that case. Now, if you look at their oxidation number or state, and it starts to move towards the negative direction, that substance is going through reduction. And it's sort of the same idea. Reduction means that you have gained electrons. So if you now gained electrons, you have more negatively charged electrons than you do positively charged protons, and you will become more negative in that case. And that's a really sort of simple way to sort of look at it. So for example, if we look at just a basic sort of reaction here, and we'll even do some balancing here. Put a 2 there and a 2 there, for example. So this is really the formation here of sodium chloride. If I can find where it went. There it is. Formation of sodium chloride. And what we want to look at is really sort of the elements on each side of the arrow here. Now, one of the things that you should know, and I think we've talked about previously, is remember that if you have something from the periodic table that is by itself, it's not combined with anything else, it's just sort of naturally how it comes, they do not have charges. So when we look at the sodium over here, that's just sodium. It is not combined with anything else. It does not have a charge. And its oxidation state would actually be 0 over there on the left. Now, chlorine, right, is one of those diatomic molecules. That's an element, and that's how chlorine naturally comes by itself. Is those ones like hydrogen, H2, N2, O2, all the halogens, fluorine, chlorine, bromine. And it is not combined with anything else, so it will actually have an oxidation state of 0 on the left-hand side. Now, if I look on the right-hand side, those two elements are no longer by themselves. They have combined together to form an ionic compound. And that is the part where they actually do gain charges, right? And the sodium in this case is actually the sodium ion, which is +1, and chloride, which is group 7, is -1. So again, they gain those charges when they come together to make an ionic compound. And we can see what's happening here by using our number line to try to figure out what is being oxidized and what is being reduced. So for example, if we take the sodium on the left-hand side, it is starting at 0, which is right around there. And on the right-hand side, the sodium ends up at +1, which would be heading in this direction here and becoming more positive. And that would tell us that the sodium in this case is going through oxidation because it's becoming more positive. So this guy is going through oxidation. And actually, one of the nice things about redox reactions are if you can safely identify that, for example, this guy is going through oxidation, the opposite thing has to be happening to the other guy. So without actually having to do anything, because I can safely know that the sodium is going through oxidation, I automatically know that this guy will go through reduction. So they always occur together. But even if you weren't convinced that they occur together or could remember that, you could still do the same thing for the chlorine that we did for the sodium. So if we look at the chlorine on the left-hand side, the chlorine is starting at 0. And on the right-hand side, it's ending at -1, which means it is moving in the negative direction. And again, when you move in the negative direction, it means you are going through reduction. Any questions on that there? So basically what is happening in this case is it is the sodium that is sending electrons over to the chlorine. And this again is the third reason why a reaction takes place, is that electrons are being transferred in this case. Any questions on that there? You can write, when you deal with reactions that are redox reactions, you could write what are known as half reactions. For example, you can take the sodium here on the left, and on the right you have 2 sodium ions because that's an ionic compound. And in this particular case, we know that this is oxidation happening. So what will happen here is the sodium will release 2 electrons, and we can put 2 electrons on the product side. And this would be what is referred to as our oxidation half reaction. And we know it's the oxidation half reaction because we actually see the electrons on the product side. And whenever you see a half reaction that has electrons on the product side, you know it is the oxidation half reaction because it's like those electrons are being given off or given away. We could also write a reaction for the chlorine here. Chlorine on the left, going to our chlorine there on the right, which is actually chloride on the right. And in this case, it is the chlorine on the left here that's going to gain 2 electrons, 1 for each chlorine that's present. And we see that this is our reduction half reaction. It is the reduction half reaction because the electrons are found on the reactant side of the arrow, like they are being gained. So these are called half reactions because if you add them together, pretty much you get the overall reaction that's going on. So if we were to take these half reactions and actually add them together, we always would want our electrons to cancel out completely. Now, sometimes when you look at a half reaction, you may not have the same number of electrons in each. So sometimes you do have to multiply a half reaction by a number just to get them to the same number of electrons. So before you would add these together ever, you always want to make sure the electrons in both of those reactions are exactly the same number. And because they are the same number, what that allows you to do is completely cancel them out. They're on opposite sides of the arrow. You can think of the arrow kind of like an equal sign in math, and you're just kind of subtracting it to the other side, and they're getting rid of each other. Then what happens is everybody on the left-hand side of the arrow stays there, and everybody on the right-hand side of the arrow that's left stays there. And since these two guys are ions, they will come together to make that ionic compound, and we get our overall reaction here by adding these reactions together. So half reactions basically show half of what's going on. One shows the oxidation part of the reaction, and one shows the reduction part of the reaction. First off, any questions on that? By the way, this is the formation of an ionic compound, which means, frankly, you should always know which one goes through oxidation because metals are always the one that loses electrons. So whenever you make an ionic compound, whenever you have a reaction like this where it's a metal and a non-metal coming together, just like we talked about with naming, metals are always the ones that lose electrons and become positively charged. Non-metals are always the ones that gain electrons and become negatively charged. So it's really super easy for an ionic sort of compound to identify what's being oxidized and what's being reduced, because it should always be the metal being oxidized and the non-metal being reduced in an ionic compound. Now, what happens if you're looking at a reaction where you're not dealing with maybe an ionic compound, but you're actually dealing with maybe just a metal on both sides? And for example, if I had iron with a +3 charge on the left-hand side of the arrow, and on the right-hand side of the arrow, I have an iron with a +2 charge. Why don't you take a moment and decide, is this thing being oxidized or is it being reduced? So take a moment and think of what it is going on there. All right, so let's take a look. Once again, if you're not sure, we can use a number line to help us out here. And guys have charges. We already know what the oxidation numbers are. The iron is going to be +3. It's the exact same thing as its charge. And the iron on the right is going to be +2, which again is the exact same thing as its charge in this case. So in this particular case, the iron is starting over here at +3. And on the right-hand side, it ends up at +2, which means it is moving in the negative direction. +2. That means in this case, it is going being reduced in this case. Any questions on that there? So it is actually receiving electrons from whatever else is there to lower its sort of oxidation state or charge in this case. Question on oxidation reduction. Now, kind of with that, there's two other terms that are sometimes used when we talk about redox reactions, and those other terms are oxidizing agent and reducing agent. And if something is oxidized or going through, or something is the oxidizing agent, it is actually the substance that gets reduced. And the reducing agent is the substance that gets oxidized. So when you're talking about the agents, it's opposite of its name. A oxidizing agent is the substance that gets reduced. Reducing agent is the substance that gets oxidized. So it is opposite of its name. So if we look at our couple of examples that we just looked at, this guy and this guy makes this. And then we looked at this here. So before we saw that this was going through oxidation, this is going through reduction. And we saw this guy is also going through reduction. So when you're asked, for example, what is being oxidized and what is being reduced, that is a different question than when you are asked what is the oxidizing agent or what is the reducing agent. So those are different questions. So in the case of our first example here, because the sodium on the left is going through oxidation, that means that the sodium here is actually our reducing agent. And the reason it is called the reducing agent is when it loses electrons and it goes through oxidation, somebody else will have to gain those electrons and then get reduced. So it is causing somebody else to become reduced when it releases its electrons. So that's why it's known as a reducing agent. The chlorine here is going through reduction, which means the chlorine here would be our oxidizing agent. And it's the same sort of explanation. In order for chlorine to gain electrons, it has to cause somebody else to lose electrons so it can gain it. So when it causes somebody else to lose electrons, it's causing somebody else to be oxidized. So that's why it's known as the oxidizing agent. Same thing here. The iron over here with a +3 is getting reduced. This would be our oxidizing agent. So if you're asked about the agent, reducing agent or oxidizing agent, it's basically opposite of its name. So the oxidizing agent is reduced, the reducing agent gets oxidized. And once again, that is a different question, as I mentioned, than what is going through oxidation and what is being reduced. Any questions on that there? Now, all of those things, the thing that is being oxidized, the thing that is being reduced, your oxidizing agent and your reducing agent, they are all found on the left-hand side of the arrow on the reactant side. So all those things are on the reactant side is where you find those things located. Any questions on that? So ultimately, these type of reactions basically take care of that idea of electrons being transferred, and that's ultimately what is happening in all these type of reactions. All right, so this is the one we were just talking about there, and again, we're getting that transfer of electrons there that is going on in this case. Here's another example. If we take a look at this one here, we have some magnesium plus some oxygen, making some magnesium oxide. So once again, if we take a look at the magnesium, it is by itself. It is not attached to anything else. So it has really no charge, our oxidation state. Same thing with the oxygen here. It is naturally how oxygen comes as O2. When we go on the right-hand side, that is an ionic compound. That means magnesium is group 2, has a +2 charge. The oxygen in this case is group 6, has a -2 charge. So once again, if we just use our little number line sort of situation to figure out what is going on here, if we take a look at magnesium, it's starting at 0 and it's ending at +2. So it is becoming more positive in this case. So our magnesium here is going through oxidation. which, by the way, would mean that it is the reducing agent because of that. The oxygen here is starting at 0 and ending at -2, which means it's becoming more negative, and that means it is going through reduction. So the oxygen here is going through reduction, and because of that, that is our oxidizing agent in this case. Once again, you don't even need the number line in this situation because this is an ionic compound coming together. We have a metal and a non-metal, and once again, the metal should always be the one getting oxidized. The non-metal should always be the one getting reduced, and that's what we see here that is happening. So again, just remembering that in an ionic compound, metals lose electrons and non-metals gain electrons. You can very quickly and easily identify what is going through oxidation and reduction in this case. Again, we could write a couple of half reactions here. These are not balanced half reactions, but we do have our electrons here on the right-hand side, which means this is the oxidation half reaction. And here we have electrons on the reactant side, which is the reduction half reaction. And obviously it's not balanced, as we would need to put a 2 across the top guy there and get 4 electrons in each. This is the balanced half reactions here. And as you can see, we actually have 4 electrons being given off, and that's because there are 2 magnesiums in our balanced reaction, and each one's going to give away 2 electrons, so that's a total of 4. And since there's 2 oxygens here, each one will gain 2 electrons, which is where we do get this 4 number here, right? And that's because magnesium is a +2, which means it has lost 2 electrons. And since there again are 2 of them, that's how we get to 4 electrons. And oxygen is a -2, which means it has gained 2 electrons. And once again, since there are 2 oxygens, it will gain 4 electrons. All right. So as I mentioned before, we really won't deal too much with other definitions of oxidation and reduction, but just quickly, just to tell you the other 2 definitions that we definitely probably won't come across all that much is, in addition to oxidation, meaning that it loses electron, which is the main definition that we use in general chemistry, it also can mean that you gain oxygen as you go from reactants to products. It also can mean that you lose hydrogen as you go from reactants to products in this case. And reduction also has similar definitions. Obviously, in addition to gaining electrons, it can mean that you lose oxygen as you go from reactants to products, and also means you could gain hydrogen as you go from reactants to products. So those are really the 3 definitions of oxidation and reduction, but pretty much throughout most of all your general chemistry career, the electron definition is typically the one that we do. Usually these guys are kind of reserved for more organic chemistry, a little bit down the road and stuff like that, is where you'll kind of see those more than you'll see the electrons and stuff like that. All right, so as we talked about in a lot of places, there are 3 real reasons why our driving forces for a reaction take place. Remember that we sort of took care of both of these with our double displacement reactions. And here with transferring electrons, that's all about redox reactions. By the way, just so we're clear, in a double displacement reaction, there is no transfer of electrons happening. So nobody's changing charges in a double displacement reaction. So when you look at the charge of somebody on the left-hand side of the arrow and the right-hand side of the arrow in a double displacement reaction, they will be the same. So there's no electrons being transferred at all in a precipitation reaction or a acid-base reaction or any double displacement reaction. Only in redox reactions do we get those transfer of electrons. All right, so as we saw earlier, a precipitation reaction is also a double displacement reaction. And remember that we have that double exchange that's happening, so double displacement reaction. And again, that is where a precipitation falls under that big classification double displacement reaction there. And again, as we saw there, we have a double exchange. And as we talked about with a double displacement reaction, that is the only type of reaction that you will always start with two ionic compounds. So when you see two ionic compounds, you should know that it's going to result in a double displacement reaction occurring. And we should always just switch partners, basically. We talked about it a lot last time as well. You remember, if you are doing that, you want to make sure you do get the correct formulas down on the right-hand side of the arrow. And make sure you do it just like kind of nomenclature. We also saw with our double displacement reactions, our acid-base reactions, our acid-base neutralization reactions, and really here, the formation there of water is what's happening in this case. So we have two ionic compounds, once again, going to switch partners, making our water and our salt. And remember, our salt's basically where we have our spectator ions basically found in this case. All right, so now we're going to kind of talk about ways to classify redox reactions. So these reactions here would fall under the umbrella of redox reactions and electrons being transferred. So here we have this, which again is a redox reaction. This guy is 0. This guy is 0. That is +1 and -1 when they come together. So once again, if we take a look at what is happening, the lithium is starting at 0 and ending at +1, and it is moving in the positive direction. So as we would anticipate, starting at 0 and ending at -1, which is moving in the negative direction. This would then mean that the lithium is our reducing agent and the fluorine is our oxidizing agent in that case. And again, we have our electrons being transferred over to our fluorine. Again, without all that, lithium is a metal, fluorine is a non-metal. So once again, the metal here should go through oxidation and the non-metal should go through reduction. Single replacement reactions is a type of reaction where you have a certain setup, and this setup can be one of two things. We can have A plus B, C, and this can be a metal, and this will be an ionic compound. And in this particular case, the metal is all by itself, which means it does not have a charge, but it will then go in and kick out the positive guy. And that's because metals, when they do make a charge, become positively charged. And when it does so, that is when that metal will then gain a positive charge and make a new ionic compound. And whatever it kicked out will basically come out with no charge. And this is a single replacement reaction. You could also do that like that experiment we did earlier on in the semester where this guy is actually a nonmetal. And if this guy is a nonmetal, it will come in and actually kick out the negative guy. And that's because our nonmetals, when they do gain charges, will become negatively charged. And it will then gain a charge and form a new ionic compound. And whatever it kicked out would come out by itself. In order for this reaction to take place, whatever is coming in needs to be more reactive than what it is replacing. So for example, if we take a look at this guy here, we have zinc, which has no charge because it's by itself. Hydrochloric acid is really ionic, which is a positive negative thing. This tells us this is going to be a single replacement reaction because that is the only thing that has that set up. And what's going to happen here is the zinc's going to come in and kick out the positive guy. which is the hydrogen. And when it does so, the hydrogen will come out in its natural state, which is hydrogen gas, and you'll see bubbles that occur. And the zinc at this point will now gain a charge of +2, and the chloride will still be -1 in this case. So this is a single replacement reaction. This is still a redox reaction that is happening. If you take a look at the zinc here, the zinc is starting at 0 on the left-hand side and ending on the right-hand side at +2. The zinc here is going through oxidation. And if you look at the hydrogen in this case, the hydrogen in this case is starting at +1, which is over here, and ending at 0, which is to the left and becoming more negative. So it's actually the hydrogen here that is going through reduction in this case. How about the chlorine on both sides? Did the charge of the chlorine change? Charge of the chlorine did not change on both sides. It's -1 on both sides. There's nothing happening to the chlorine. It is actually a spectator ion, just like we saw with double displacement reactions. You could, for example, write this reaction as a total ionic equation, and that would be zinc plus 2 H pluses plus 2 chlorides. And since that's a gas, we would keep it together. And we would break apart this guy into a zinc with a +2 charge and 2 chlorides. And this would be our total ionic equation that's happening. And if you look at it just like we saw on our double displacement reactions, we actually see the chlorine here is actually our spectator ion. It's not changing. That actually only has one spectator ion in this case. They cancel out, and that leaves you your net ionic equation, which is zinc plus 2 H pluses. Go to H2 and zinc here. And this is our net ionic equation. Now, sometimes people will ask, how come the zincs don't cancel out? And the reason the zincs don't cancel out is on the left-hand side, it is not an ion. It has no charge. And on the right-hand side, it does have a charge. So they are not ions on both sides. That is why the zinc wouldn't cancel out here. So ultimately, what's happening here is this zinc is sending 2 electrons over to the hydrogens. And when each hydrogen gains 1 electron, it will become H2 in this case and make that gas that forms. Question on that there. Now, again, in order for this reaction to take place, it means that the zinc is more reactive than the hydrogen. If you did this exact same reaction with copper and try to react with HCl, you would get no reaction. And that would mean that in this case, copper is less reactive than hydrogen, and it will not replace the hydrogen in this case. Questions on that there? Now, how do you know if something is going to replace another element? You will sometimes come across something that's known as an activity series. An activity series, a basic one, is just a listing of elements. Somewhere in the middle, you'll have things listed below it. So, for example, you might find like above hydrogen or listed below hydrogen. And when you look at an activity series like this, anything that is higher on the list will replace anyone lower on the list. And obviously, the opposite of that is any one that is lower on the list will not, a lot of L's there, will not replace anyone higher on the list. So that's why, for example, like we just saw there, if we had our zinc plus our HCl, we are good to go on this reaction. The reaction will take place. But again, if we try to do it with copper, it is less reactive than on hydrogen. So again, here, not going to take place because of that. So sometimes you will come across maybe an activity series, and that's sort of how you look at it. Kind of higher on the list, more reactive than anything lower on the list. And those reactions would occur if the thing higher on the list is coming in. If somebody's lower on the list coming into somebody higher on the list, they will not replace. By the way, as we saw with our experiment that we did a while back, group 7 on the periodic table, fluorine, chlorine, bromine, and iodine. We already know the activity of that if you remember that experiment. Hopefully you do. Reactivity increased as you go up on the list. So the periodic table for group 7 for our non-metal interactions is sort of what happens. So reactivity increases as you go up on group 7 on the periodic table. Any questions on single replacement reactions here? All right, so single replacement reactions, like I said, are a part of redox reactions. The next type of reaction we're going to talk about is, since I wrote on this page, let's get rid of that there so you can see, are combustion reactions. And combustion reactions also fall under the big redox sort of category. So redox reactions here are combustion reactions. And that's a more specific classification. Now, when we talk about combustion reactions, there are two types of combustion reactions that we talk about. One is probably, I would say, 99% of the time when somebody is talking to you about a combustion reaction while you're having that conversation, I'm not sure, but when you have that conversation, sometimes people refer to it as an organic combustion reaction. And what that means is you're starting with an organic compound, which has carbon, hydrogen, sometimes oxygen. So that is an organic compound, and that's an organic compound, basically carbons and hydrogens here. And in that type of combustion reaction, there's basically three things that always appear in the reaction, and that is O2 on the left, CO2 and water. So that's like a no-brainer there. O2 on the left, CO2 and water on the right if it's an organic combustion reaction. That's pretty much what it's always going to make in these reactions. Occasionally you will not get CO2, but sometimes in what is sometimes referred to as a incomplete combustion reaction, you'll sometimes get carbon monoxide rather than carbon dioxide, but probably 99 times out of 100, you're going to get CO2 plus some water there. Now, I would say most of the time, those are the reactions that people sort of are talking about when they mention combustion reactions. But the true definition of a combustion reaction, and really the only thing that you need for it to be sort of a combustion reaction, is O2. So basically, if you have a reaction that has O2 on the left-hand side of the arrow, it essentially will be a combustion reaction and can be classified as a combustion reaction. So that's sort of your really just general definition of a combustion, is pretty much you just need kind of O2 there on the reactant side, and it can be classified as combustion. But once again, I would say most of the time people are kind of talking about these type of combustion reactions that involve organic compounds. Like methane, like when you light your Bunsen burner, that is a combustion reaction that's occurring in that particular case. Methane plus oxygen, a little bit of spark makes fire. And the next type of reaction that falls also, once again, under the umbrella of redox reactions is synthesis or combination reactions. So the way you can recognize a synthesis or combination reactions are you take two things and you make one thing. So basically combination or putting those things together. So two things that make one thing is your classic sort of combination reaction or synthesis. So here we have H2 and O2. Two things making one thing, water, is definitely a combination or synthesis. This one we saw earlier, sodium and chlorine. Two things make one thing are a combination or synthesis reaction. These guys are still a redox reaction that's happening. If you look at the water formation here, the hydrogen on the left is 0 because that is naturally how it comes. The oxygen on the left is 0 because that's naturally how it comes. When you make water, water is basically H plus and OH minus, which means this is +1 and -2. So again, if we kind of go to our little number line thing here, we see when we look at the hydrogen is starting at 0 on the left and ending at +1 on the right. So it's becoming more positive, which means the hydrogen here is going through oxidation. The oxygen on the left is starting at 0 and ending at -2. So becoming more negative and going through reduction. So although it is a synthesis or combination reaction, it is also really what's happening, a redox reaction. Electrons are being transferred from the hydrogen to the oxygen in this case. So really electrons are heading in that direction. This is the one we saw earlier, also heading in that direction. So as you can see, you can classify a reaction in a few different ways depending on what you're looking at. For example, if we take a look at one we just saw, which was like magnesium plus some oxygen, makes a little magnesium oxide in this particular case. This is definitely, as we talked about, a redox reaction, as again 0, 0, +2, -2. It is also a combustion reaction because, well, frankly, it has oxygen, so it can be classified as a combustion reaction. And if my eyes don't deceive me here, this kind of looks like two things that make one thing. So it can be a synthesis or combination reaction as well. So you definitely have multiple ways you classify the same reaction depending on what you're looking at. I would venture to guess most people will probably classify this as a synthesis or combination reaction, but it can be classified as those other two types of reactions as well. So there are definitely multiple ways to sort of classify a reaction. You would want to choose whichever way seems the best to you in that situation. Now, a decomposition reaction is basically the opposite of a synthesis or combination reaction. So in a synthesis or combination reaction, like we just talked about, we kind of put two things to make one thing. In this case, we're going in the opposite direction. We're going to start with one thing, and it's going to break apart into two or more things. So kind of synthesis and combination, you're putting it together. Decomposition, you're basically breaking it apart. And this is still a redox reaction. So this is still overall a redox reaction that is happening in this case. So if we look here, we got one thing making two things. So that definitely is a redox, a decomposition reaction. We got a little potassium chlorate breaking apart into KCl plus some oxygen. Maybe a 3 there, maybe a 2 there, maybe a 2 there. This is, again, one thing making two things, a decomposition reaction. Carbonic acid, which is oftentimes formed as a result of an acid and a carbonate coming together, quickly breaks apart into water and CO2 gas. So again, one thing making two things. So these are all examples of decomposition reactions, breaking something up into smaller. They are still redox reactions here. So the water on this side is +1, -2 for the oxygen, 0 and 0. So we do have electrons being transferred. Same thing if we look over here. This is, well, this is +1, this is -2, and not really important for our scope of practice here, but believe it or not, the chlorine here actually has an oxidation state of +5. And in this particular case, we have -1 and +1 and 0 in this case. So in this particular case, we do have the chlorine going from +5 to -1, And again, if you did that on your number line in this case, started at +5 to -1, or sorry, to +1, and the chlorine is actually being reduced. The oxygen here is going from -2, which is over here, to 0, and it is being reduced, or being oxidized in this case. So it is still going through a oxidation and reduction type of situation. Any questions on that there? So decomposition, breaking it apart. Synthesis, combination, puts it together. Single replacement and combustion reactions are all basically redox reactions. So to summarize here, two big classification of reactions: double displacement, and more specific ways to classify a double displacement reaction is a precipitation reaction, which obviously accounts for our solid being formed, and our acid-base reactions, which basically account for water being formed. Once again, none of those involve any type of electrons being transferred, so nobody's transferring electrons in those reactions. Redox, big category, which is all about electrons being transferred. We have more specific classifications that fall under that. That is our synthesis reactions, our combination. That is our decomposition reactions. That is our single replacement reactions. And that is our combustion reaction. So again, more specific classifications that fall under the big category of redox and electrons being transferred. And again, more specific classifications there on the left of the big category of double displacement reactions. Any questions on any of those there? All right, we will lay it up there, I think,